Alright, finding areas of polar functions. They're finding areas involving polar functions, both inside and outside. In this case, we've got the area enclosed by r equals sine theta plus cosine theta. As you can see, first thing is try to get an idea for what this looks like by plugging in a few points. We end up getting these square points starting here and going around counterclockwise. Here we see that we actually trace the entire shape out within 0 to pi units. So theta only goes 0 to pi. Again, it doesn't take a computer algebra system or Mathematica to show that, even though we can plot it within Mathematica and change our values to pi in this case to see that indeed it's plotted out from 0 to pi. But then we have our simple integrand 1/2 r squared, plugging r squared in and using a couple trig identities. First off, sine squared plus cosine squared equals 1. Secondly, our 2 sine cosine is equal to sine 2 theta, which makes our integration pretty simple. And our answer of pi over 2. We can verify this in a few different ways. First off, we can verify what the diameter is. Diameter is going to be our furthest reaching r value in this case. Out to here, this r value is root 2, which means our radius of the circle is root 2 over 2. Thus, pi r squared, or pi times this radius squared, ends up being 1/2. Or sorry, pi over 2. Just using the area of a circle. We can also verify that down here with by changing this stuff, these polar coordinates, into Cartesian coordinates. In doing so, we've done this trick before. R involves just a radical, so in order to avoid that, we'll square both sides, or multiply both sides by r, giving us squared on one side and an extra r on the other. By distributing this r, we end up with r cosine and r sine, or x and y, and that r squared is equal to x squared plus y squared. So we get this equation, which we can then complete the square in this step and see that we've got a circle centered at 1/2 of radius, root 2 over 2. Again, plugging that in for the area of a circle, pi r squared, we end up with pi over 2. So finding the area within circles isn't the worst thing to do, or the most difficult. It's just dealing with the intricacies of the trig functions is what tends to be most difficult. In this case, we've got R1 and R2, two different curves, similar to Cartesian functions, where you can take the integral of f of x minus g of x, or the big one minus the small one. We can do the same, use the same methodology here. But in this case, it's actually easier to find these two different areas. We've got the red area and the green area, as denoted below. And those areas are for different curves. Okay, separated here by the line at pi over 6. We can find pi over 6 and 5 pi over 6 through solving the equation when those two curves are equal, the intersection points. We're finding these intersection points. Once those are found, then we've got our limits of integration. for those two different figures, and it's just a matter of assigning R1 for that red one. R1's the circle, so the outer dimension for that particular portion is the circle, or R1. Outer portion for this portion of the curve is the cardioid, or R2. Then it's just a long, tedious matter of integrating. In both cases, we end up using the trig identity for excuse me, integrating sine squared. That's the 1/2 1 minus cosine 2 theta. And you can see through all the work we end up with two different values here, the red one and the green one. The red one, very small, very slim, is 0.2 roughly. The green one, quite large, is about 0.7. So together, the red and the green, we get about 1.9. As usual, you can ask yourself if that makes sense. And we've got this figure here that's being traced out that we're saying has an area of about 2. Well, we go out to a little bit past 1 on the x-axis and up to 2 on the y-axis. So it should be a little bit less than 2, so that makes sense. But the area enclosed by, or the shared interior of these two curves, means that we have to take the area that we found, this area, and multiply it by 2 in order to get both of these. We had that 2 out here in the beginning, and you can see 2 times that area is roughly 4. Again, we go out a little bit past 1 on the x-axis on both sides, so it's about a distance of 2 times 2, or roughly an area of 4. So our answer again makes sense. These tend to be the difficulties with the polar areas, not the fact that we're taking the difference between the curves or trying to find the area of the big one, subtract the area of the small one, but rather dealing with these trig identities and trig equations, and then very long integrands tends to be the difficulty. As usual, if you have any questions, please let me know.